Okie dokie. I'm actually surprised this is not the worst attended lecture I've had this term. And Thanksgiving is tomorrow, so thank you people for showing up. Maybe that means some of you are excited about what we're going to talk about today, or maybe you just have nothing better to do because everyone else is out of town. So, either way, win for me. Have an appropriate audience here. So, today is a sort of what I usually in the past have called an optional lecture in my class. So many people who do data work of some kind or do go through their entire careers working with data may never actually do any mapping or may not even work with any geospatial data. But the sorts of things you can do with geospatial data and the way that you can link data sets together make it something I think is worth everyone taking a look at. If nothing else, maybe it will give you ideas for how you can incorporate geospatial stuff into your work that isn't otherwise geospatial, or maybe you just want to use it to make pretty pictures that will attract people to your posters and your articles and things like that. The nice thing about working with geospatial data in R is that it's become very, very easy to do, so the sort of barriers that people used to face in getting into GIS software and things like that, they don't really exist anymore in R. It's just trivial to work with geospatial data, so you really shouldn't avoid using it because it's difficult or because you're worried about things like GIS. I'm going to go through sort of terminology of geospatial data, how you can download it, how you can plot it, how you can integrate it into things we've used in this class before. And we have plenty of time throughout this if you want to stop and ask questions and things like that. This is not like a super long lecture. It's sort of optional, bunch of fun stuff. Yeah. So, today's basic kind of overview here is we're going to start with basic mapping in ggplot 2. So latitude and longitude are just x and y coordinates, right? So you can give latitude and longitude to ggplot without telling it it's geospatial data of any kind and plot stuff right in it like it's anything else. It just kind of works, right? I'm going to talk about GGMap. GGMap is a package that will allow you to put maps from things like Google Maps and things like that in the background of your plot. So you could plot normal ggplot graphics on top of maps, and it takes care of figuring out how your latitude and longitude line up to actual like Google Maps and OpenStreetMaps, and just lets you plot on top of it pretty seamlessly. I'll talk a little bit about labeling points. Sometimes you want to have labels on geospatial points, things like that, and the ggRepel package. This is sort of basic mapping. Anyone would very easily be able to do this, and there's really no reason not to. I'm then going to, for sort of the second half, or almost 2/3 of this lecture, go into more advanced mapping. So more advanced mapping is essentially doing GIS-type work in R, particularly using the SF package. I'm going to talk about what simple features geometries are, how to use the SF package, and then I'm going to talk about a package I really like that links up to the tidyverse of packages and the SF package called Census. Census automates the process of obtaining data from the U.S. Census Bureau. That is the decennial census, ACS census, ACS, so American Community Survey, for people unfamiliar, data, and formatting it in a nice tidy format, and also grabbing the geometries that allow you to plot things like census tracts, counties, cities, states, all that stuff in the United States. It all comes together in this one package that's really user-friendly. Even when I'm not using any census data, I very often get my geometries for things like census tracts using Census, because it's just like one line of code will pull down all the census tract geometries that I need and format them as I need them. It's really cool. Okay, so a quick plug before we start. If you want to get deep into mapping GIS and geospatial analysis in R, especially geostatistics, just get this book. Just pick this book up. This is by Van Pabesma and Gomez Rubio's Applied Spatial Data Analysis with R. It is basically the Bible of geospatial analysis in R. Most of the geospatial packages in R were written by these three people, so they generally know what they're talking about. It's a little bit of an older book, so it uses mostly the SP package, which I'll talk about a little bit rather than SF, but all the statistics and stuff like that hold up, and this is generally a really good book. Another good resource, which is somewhat more up-to-date, is rspatial.org. It's a massive repository of tutorials and information and working with spatial data in R. It's just huge, has tons of stuff on spatial statistics, which I won't even touch today. If you're interested in learning spatial statistics, John Wakefield teaches statistical methods for spatial data, which is a pretty good class. It's pretty challenging, and it focuses mostly on statistics rather than on mapping. But if you're going to work with geospatial data in a statistical framework, you have to learn statistical methods for geospatial data. They're different from other sorts of data. because they have, if you're familiar, they have autocorrelation, but autocorrelation in multiple dimensions simultaneously. That's really hard to account for using conventional statistical methods. So you have to figure out how to do things like latent Gaussian fields and stuff like that, which is cool, interesting to learn about, but you're probably not going to get it in any other class you take. Lastly, if you want quick introductions to using GIS software, so not specifically using R, but rather using dedicated GIS packages, CSE offers free workshops in QGIS or ArcGIS. Because I think proprietary software is terrible and you should not use it, I recommend using QGIS because it's open source, it's free, has a great community, and has pretty much all the features of ArcGIS. For many applications, QGIS is actually substantially faster than ArcGIS, except for certain things. Yeah, I like QGIS. Most of my friends who work in surveying or work in geospatial data do most of their stuff in QGIS. Okay, so basic mapping. By basic mapping, I mean just throwing coordinates into ggplot2 and maybe hucking a map into the background. Okay. Back in week 5, we looked at some SPD incident data. So it was one day of every incident the Seattle Police Department responded to 911 calls. Actually, I think it's exclusively 911 call data. Everything SPD responded to in like March 25th, 2016. It's actually still pretty big because it's a large city. Police respond to a lot of things. I'm going to use these data because these data have latitude and longitude in them, so we can do some fun plotting with these things. If you want to load it up, it's on the website right here. Okay, so this is what these data look like. They have a lot of terminology in here that's sort of police specific when they say things like event clearance code, event clearance description. Clearance descriptions are essentially police will respond to an event. When they get there, even though the call might be for one thing, after the event is resolved, they will report what actually happened, and then that is the event clearance code. So when an event is cleared, they label it with something. So they might show up because there's an argument. By the time they get there, somebody's been stabbed. It's no longer like a disturbance. It's now instead an aggravated assault. Right? They've got that. They have time and date data here on, where is it? Event clearance date is time date information. They have things like the block location, which is something colloquially would be useful for us to know. I mean, if you know Seattle well, if you get something like, oh, South King Street and 8th Avenue, you know exactly where that is. That's not practical for mapping, though. The nice thing with Seattle is Seattle by default provides longitude and latitude of all of the events down to super precise locations. So we've got that. This is useful to us. We can do plotting with this because these are just numbers, right? We have an X coordinate, we have a Y coordinate, we can make a map out of this. Okay, so coordinates like longitude and latitude, you can just throw them into the AES in a ggplot as X and Y values, and it will plot a map. So if I just say ggplot, SPD raw data, AES, my X is longitude, my Y is latitude, and I just do geom_point. Here I'm doing coordinate fixed, which makes it so that the axis, like a change of 1 unit on X is the same distance as a change of 1 unit here to make my plot even up. Otherwise it would squish it to be kind of square. Give it a title, being classic. If you know more or less what Seattle looks like, you'll realize this is downtown right here. This is the port and water here. West Seattle's over here. That's Alki, right? You've got sort of this outline of Seattle, okay? You probably wouldn't provide this to someone as a map of crimes in Seattle because you can't actually see Seattle. You just see where there are crimes. So it's well defined and downtown, but you don't even see Laurelhurst up here or anything like that because nobody's committed any crimes there, so it doesn't exist here. Normally, with a plot like this, what we would want is to plot these points on top of some existing map that will give us an idea of where these crimes are happening in the city. To do that, we can use the package GGMap. So, GGMap is a package that works with ggplot to plot your spatial data directly on top of images of maps that it obtains from Google Maps, OpenStreetMaps, or Stamen Maps. These images are what you call a raster file. Raster is in there's something like a JPEG or a PNG image, rather than being something vector that's drawn as lines and points the way ggplot draws things. So it's a layer that will serve as a background, and ggplot will draw stuff on top of it. Okay? This lecture today used to focus more on GGMap, but Google went and did something that upset me, in that now if you want to download most maps from Google and you want to plot data onto Google Maps, you now need an API key from Google that has a credit card linked to it to make those requests. I'm not going to teach people things that require them to sign up with a company and give them a credit card number. So we're not going to be doing those queries. That forced me to redo this entire lecture for today, basically. Very annoying, but took it as an opportunity to teach you guys some cooler stuff today anyway. So anyway, what GMap will do is it will query servers for a map using the getMap function at a specific location and scale. If you have a Google Map API key attached to it, you can just give it Google Maps search queries, and it will display the same map you would see in your web browser if you made that query to Google Map. The exact same map, because it's actually going through the same interface that your web browser does to download maps. If you don't have it linked to an API key, you're limited to instead providing a bounding box of coordinates. A bounding box is a square that defines where all of the coordinates in some set exist, and it's usually set as being the difference between I think it's usually, I don't know if it's upper right and lower left, or if it's upper left and lower right. I think it's actually upper right and lower left, and this is a pile of crap. Okay. You imagine that you can define a square or a rectangle with exactly 2 points. If you know this point down here and this point up here, you don't need to know this point and this point because these lines are parallel, right? So a bounding box, you provide this coordinate, and then it will just grab, with GGMap, it will grab all of the map that sits inside this rectangle and plot it. Okay. So GGMap then will plot that raster image, that bitmap image, or it's basically they're all ping images if you're familiar, as a ggplot object that it puts all the way in the background. Every other layer will be plotted on top of that. And because it's working in a ggplot sort of framework, you can add any ggplot layers like points, density plots, text annotations, titles, labels, all these things on top of those. Right? It also includes additional functions for interacting with Google Maps, OpenStreetMaps, things like that. If you do have an API key linked to GGMap, you can make queries that will do things like get the distance between 2 points by car or bike or walking, including the time it takes to get from that point to that point. This is pretty neat stuff. But you need that API key, and I don't want to get into getting API keys and making people sign up with a credit card today. Okay. So, to do installation of GGMap, right now the GGMap package that is up on CRAN, sort of where by default R goes and looks for a package, is somewhat out of date. If you want the current version of it, you have to download it directly from GitHub, which requires a package called DevTools in R. You should have DevTools installed anyway. It doesn't come by default in R, but everyone should install DevTools because inevitably if you spend much time working in R, you're going to want to download packages from people's GitHub repositories instead of just CRAN. I download stuff from GitHub all the time. A lot of it's just because I want new features that are in packages that haven't been released on CRAN yet. But basically, if you have DevTools, you can say install GitHub. You give the username of the GitHub user / the repository name, and it will install that package directly like that. This is something that's important to know how to do. Okay. Then you just load it, library GGMap. If you install from GitHub like this, it may have to compile on your computer. Basically, if you see errors or things you're not expecting when you run this command, let me know. This is particularly going to be the case for people on pretty much every system. If you're not on a Linux machine, you're going to get some kind of a thing popping up. Macs, you have to install some developer tools to compile things from the command line. Windows, you will have to have RR tools to do compilation. Don't want to teach that in the class because I don't want to get people into how do compilers work. But if you have questions, ask me. Yes?
I was looking at this and I just did install ggplot just from CRAN or GMap.
Yeah.
So
it'll work.
Yeah, what's the difference? That's more up to date?
Yeah, so the one on CRAN, I believe, is about 2 years old.
Okay.
And so it doesn't, it will fail when it makes Google Maps queries because Google changed their API calls. This is something really, really common when you're working with R packages or any kind of software that has to make some sort of a call out to some companies like API, their application programming interface, which I'll talk a little bit about. Basically, companies like Facebook is the bane of my existence because they change their API like on a monthly basis. Every time they change their API, the list of commands you can basically send to them to get data are different every time they change the API. This drives you insane because it forces you to rewrite your software. It's really hard to go through the testing process to upload a package to CRAN. And the developers here, it just has changed so rapidly that they're sort of like, okay, we want the stuff to stabilize before we submit it to CRAN, because otherwise it'll be wasted labor, because we'll have to keep changing stuff. Like, they've been making updates to GGMap up to, I mean, the most recent one is like late last month, and things look like they might be stabilizing, but, you know, who knows. Yeah, APIs are moving targets, so often with anything that works with an API from some company, Facebook, Instagram, Twitter, any of that kind of stuff, you often want the development version of the package on GitHub because it will be up to date with the current API. Twitter tends to be pretty nice in that what they do is they allow you to use legacy API calls where you can say, okay, the API version I wrote the software for is 2.7.9.4, so let me make calls on that even though the API is now at like 3.1 something. That's really nice. Twitter is still garbage, but you know, at least you can get data from it. Okay. Google did not do that nice thing, which upsets me. Anyway, so the neat thing with GGMap is it has these quick plotting functions that will just generate the map you're asking for with minimal intervention on your part. So the function QMplot is quick map plot. It doesn't, the syntax doesn't quite look like ggplot syntax, but it's actually a quick wrapper that will make a ggplot. What it does here is you can just say QMplot data equals whatever data frame you want, your X and Y aesthetics, and then you could set things like color and alpha. These arguments here are things you would normally see inside of AES, but you can just give them as straight arguments to QMplot. It will pass them to an AES sort of under the hood. So all I gave it were numeric latitude and longitude. I didn't say it was in Seattle. I didn't say anything like that. I just gave it the latitude and the longitude. What it does is it figures out this bounding box based on the maximum and minimum values in latitude and longitude that you gave it, goes and grabs a map in that bounding box. So in this case, our data are all in Seattle. So it went and got a bounding box that is at the minimum and maximum values of our latitude and longitude, created a little bit of a buffer, extends it out, and then plots this map in the background for us. And this is a pretty map. The default map, it actually looks really nice. It's a map from Stamen Maps, which makes sort of more design or civil engineering looking maps and things like that that are pretty and they look nice in publications. All of our data are plotted exactly as before, where we see a cluster in downtown and everything, but it's now scaled everything by latitude and longitude appropriately. It hasn't stretched or shrunk this in some inappropriate way, and all of our points are on a real map. And we know it worked because we can see none of our points are in the water, everything's lined up properly, right? This is pretty cool. It's incredibly easy to get maps of places. You could give this additional arguments to get different types of maps, change the zoom, change the projection, and things like that, but by default, it just sort of works. Any questions about that?
Is that part of GGMap?
Yeah, it's a GGMap function. QMplot. Yeah, just works. I love it. Okay, so QMplot and the function QMap, which I didn't show now, QMap displays that background map, but doesn't plot any data on top of it. It's just for getting images of maps. That one requires an API key because it goes through Google Maps. Anyway, they're wrappers for a function called getMap. So if you want to know the arguments you can give to QMplot, something like that, you can do $getMap, and you'll see it has a lot of arguments that do a lot of different things. If you have a Google API key attached to it, you can just give it a location and a zoom level, and these correspond to whatever you would put in the search bar on Google Maps and whatever zoom level you ask for. This is directly Google Maps queries. Okay? Alternatively, you could provide a location as a numeric vector of longitude and latitude, and that does not require a Google API key and will just return that bounding box, which is what I did basically on the previous one. You can specify a source, which are different maps that it will go and get. So Google Maps used to be the default. It has general purpose maps. You can get street maps, you can get satellite maps, terrain maps, contour maps from Google. There's also OSM, OpenStreetMaps. OpenStreetMaps is a free and open source alternative to Google Maps that is crowdsourced. So for some things, OpenStreetMaps is actually better than Google Maps because Google Maps is all curated and done by in-house staff at Google, which means there's some things they don't put on their maps. OpenStreetMaps is kind of the Wikipedia of maps, and people can just put whatever the hell they want on there, more or less. It's pretty good. There's also Stamen Maps. Stamen is the default we saw over here that makes these kind of pretty minimalist maps. They also have other things like watercolor maps, things that look hand-painted. They have like architectural-looking maps and things. Stamen's pretty neat. I like some of the Stamen maps for use in publications if you want to see a background because they're minimalist and they look good. You can also then specify down here the specific types within these, like I said. So for Google, you get terrain, road maps, satellite maps, hybrid. For Stamen, watercolor, toner. This is toner map. Toner, toner background, toner light. You could also specify whether the map should come in color or in black and white. Most journals, even though they're all online, print everything in black and white, even online, so you'll have to want black and white. So, a lot of features. Any questions about that stuff? It's kind of thing to tinker with. Yeah.
I know one of my friends works with GIS, and he said like the Google API keys are now pretty expensive, so we can use OSM though, and that's free.
Yes, OpenStreetMap is free. So the Google API keys are expensive not to people like us, because for free you generally get up to about 3,000 queries before they start billing you. For somebody like me, that might add up rapidly on some projects, because 3,000 queries, if I'm doing like plotting points and stuff, can be a huge pain if I have to like map. So by 3,000 queries, I mean like if I'm giving it a written address and I want to convert it to longitude and latitude, every one of those queries would eat up one of those. 3,000, that eats up pretty fast. But for most people, actually querying a map, like downloading a map image, does not eat into those 3,000 queries. So you have to have the credit card there, but almost all people would never get a charge on the credit card because they have such a large number of free ones. For people who do hardcore geospatial, like GIS work, it can add up. It will, though, be much cheaper than Esri's version of this thing. Esri, who makes ArcGIS, charges a goddamn fortune for queries like that. And Google's basically putting them slowly out of business. But anyway, yeah. So yeah, most of the time it's free, but I don't like make people being like having to sign up for a credit card. It's kind of stupid. Okay. So you can add things on top of these maps generated by QMplot. So this is the same, basically the same QMplot map before that I had. But now what I want to do is, instead of plotting all of the points on top of it with GeoPoint, I'm going to make a density plot of the density of criminal incidents in Seattle on this particular day. So this geom here, stat underscore density underscore 2D, is a two-dimensional density plot. The way densities work, if you're not familiar, got an eraser here somewhere. Every one of these markers is a giant pile of crap. Okay. So imagine you had a whole bunch of point data that looks something like this. What the density is going to do is it's going to more or less imagine that it assigns a circle around every one of these points. And that wherever one of these is, imagine that it's stacking these circles up. So here, there's only one circle anywhere in here, one circle here. But here, there's two overlapping. So you would imagine this is a height of 2. This here is only a height of 1. That's what the density is doing. It's just stacking them up in some distance away from the points. In reality, on something like this, it's using a thing called kernel density, where instead of this being a circle, it's instead a curve like that. So if you stack a bunch of these curves up like this, like the total shape of this is just going to look like this, and it's going to be much higher right there. Like this is the sum of these two curves. It's a kernel density. Anyway, that's all it's doing. It has some bandwidth around each point. It stacks all these circles up, and it generates some sort of density plot. I'm just saying the fill for this, that is the color, is going to be determined by stat level. Stat level is telling ggplot that I know this particular geometry stat density calculates a parameter called level. So I'm saying I want to plot the statistic level, which is calculated by stat density, and I want to assign the fill. The fill is sort of the background color of something. In this case, it's a polygon it's going to draw. Then I say here, scale fill gradient. Scale fill is going to control how this fill, the statistic, maps onto different colors. And here I'm just saying I want low to be white, mid to be yellow, high to be red. Because it's partially transparent, the white is just going to do nothing. It's going to be invisible. But there's going to be yellow and there's going to be red. And then I have over here my density plot. In this, it's a little zoomed out, so it's hard to see, but it's sort of in like very light yellow, transparent. There's one next color, a next color, a next color, a next color, a next one. There's only like 6 or 7 colors actually being plotted in there. It's kind of doing like tiers. So it looks like a layer cake, getting narrower from bottom to top. Yeah, but that's a density plot. If you work much with geospatial stuff, especially point data, you'll very often want to convert a whole bunch of points to a density like this, because if we go back to a plot like this, okay, we know there's a lot of points over here, but it's kind of hard to compare like how many points there are in this area because they're all overlapping towards like these less dense areas. This takes care of the fact that they all overlap and converts into some continuous metric. Like looking at this, I know that down here in downtown, in this rough area, there's roughly 300 incidents being mapped downtown in there in these data. I sure as hell would not know that there's 300, some incidents down there, judging by that just blob of purple. Okay, 2 different ways to display point data. Any questions on that? As well as ones you want to tinker with if you want to use it. Okay, so maybe you want to label the points on a map. Very often we're plotting a relatively small number of things on a map and we want to draw labels on them to highlight where they are. So what I'm going to do here is I'm going to label the assaults and robberies, specifically the ones that are in downtown Seattle. It used to be that I could have just queried Google and said, give me downtown Seattle, and plotted the points on top of it. Because that functionality now requires an API key, instead what I did is I went back to one of the maps we did earlier, which I went down to this one, and you see how the longitudes and latitudes are displayed? I just eyeballed it and said, okay, downtown is basically right about here, this like square. So I just figured, okay, that lines up to here, and about there and there. I just eyeballed it, grabbed those values as latitude and longitude, and I just do a filter. I say I want everything to be between 47.58 and 47.64 latitude, and between negative 122.36 and 122.31 longitude. This is me creating my own bounding box for my data and filtering my data down to it. Then I make a quick data frame here that's just the assaults and robberies in the data set. So I say I'm going to create a new variable that is a label. This label is going to be whatever the event clearance description is, if it is an assault or a robbery. Otherwise, nothing. And then I filtered out all the ones that are nothing. So the data set is just assaults and robberies with a label that is the actual type of assault or robbery that it is. I can then plot this. So if I use geom label on top of my sort of previous plot, it will generate labels for all of those individual events that happened on here. You'll see there's a lot more dots here than there are labels. The reason is I'm still plotting my original data that isn't just assaults and robberies, but I've now only drawn a label for assaults and robberies, and there's only like 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's only 9 of them in downtown. Okay? In this case, to make sure that my labels do not come in as being the same color as my points, I had to put color and alpha in this I command. Just do that, and it works. I have no idea what the logic behind that is, but that's the way QMplot does this for controlling label and point coloring. I tells it to limit it to just being the points. Okay.
What's it do otherwise?
Otherwise, these labels would be transparent red, because 50% transparency and color red. It would propagate that AES to labels. Now, QMplot isn't perfect, behaves a little strangely, so you learn some tricks to get around it. Okay. Thing is, though, all of these are sort of plotting on top of each other, so it's hard to read some of these labels. We might want to make them repel each other, like make them push each other apart. Now, back in the day, before I discovered that there was a package that exists to do this, I tried to program a sort of a routine that would automatically push all the labels away from each other in a nice uniform format. Something which I discovered after much coding and struggling and weeping softly over a drink is that it's really hard to program gravity models to do that. So thank God there's a package that does this for you. The ggRepel package, which you can download much the same way you download like ggmap, do install.packages ggRepel, has functions that have built-in sort of gravity models that push away labels from each other to make them all visible, and they kind of fail gracefully. In this particular case, I have lots of labels, so many that they're going to have to overlap a little bit. It actually allows them to partially overlap where it's reasonable while minimally blocking them. It's a pretty smart package. To do it, all you have to do is replace the geom label we used over here with geom label repel, and it will push those labels apart. It's pretty intuitive. Normally, you don't want to plot plots with labels where you have so many labels that you can't see the map underneath it, so often repel is going to be kind of unnecessary, but sometimes you've got a cluster and you want to do this. Another neat thing ggRepel does by default, it's kind of hard to see on this map, but when it pushes some label a ways away, it also draws a black line pointing down to that point, so you can see what it is that it's pointing at. Neat little package. Okay, so that's everything I'm going to talk about basic mapping. Are there any questions about GGMap or that stuff? For the most part, it just works. But to use it, you need latitude and longitude, and you probably aren't going to be doing anything super complex. This, though, that I'm going to talk about, advanced mapping, is essentially doing GIS-style operations and actually using real GIS data in GIS formats inside of R, using the SF package. So, there's some terminology you'll want to know about geospatial data I'm going to talk about. I'm going to talk about simple features, geometries. I'm going to talk about coordinate reference systems and shapefiles. First, the SF package, it used to be up until fairly recently, I guess up until about a year and a half ago, everybody pretty much worked with geospatial data in R using a package called SP for spatial. The SP package was pretty great. It was very powerful, it's very fast, it still is very fast, but it's complicated, it's old, it's been around for 15, 20 years, and the syntax looks like it's been around for 15, 20 years. It predates the tidyverse, so it doesn't link in with all that stuff. It doesn't play nicely with ggplot. And one big thing is it does not store data, that is geometric data in it. It doesn't store it the same way software like ArcGIS or QGIS stores data. So, enter the SF package. The SF package is a sort of replacement for SP that implements the ISO standard of simple features, which is what now all GIS software uses as a method of storing geographical information. It's basically an R package that uses the same methods for data storage that every GIS package out there uses. This is nice because it means that you can just speak directly to GIS software and back and forth. They speak the same language. Another nice thing is that SF is integrated into the tidyverse. It includes things like geom_SF to plot geometric data in ggplot. It plays nicely with dplyr. It plays nicely with ggplot. This is pretty great. It is a little bit new. Sometimes it's a little weird in its behavior. It gets better every day, and honestly right now it's pretty stable and good. I don't no longer run into errors regularly with it. And it's going to completely replace SP eventually. The people who are writing SF, the main authors and contributors to it, are the people who wrote the SP package and also the people who wrote that book that I showed on the first slide, Applied Spatial Data Analysis with R. It also, however, includes people like Hadley Wickham and Garrett Groleman, people who are big people in the tidyverse as well. So it's bringing together the big minds in spatial data analysis with R with the people who do all of the main data programming packages in R. It's this wonderful fusion of essentially the best minds of this stuff in the world of R. Because it's the new standard, I'm going to ignore SP completely, and I'm only going to talk about SF today. Sometimes you'll find functions that require you to use SP for somewhat advanced spatial stuff. Every few months, they start disappearing more and more. I'd say that currently the half-life on SP required functions is maybe 3 months, like they're declining quite rapidly. Sometimes you'll have to use SP though. Go get the book if you want to use SP. Okay. Simple features. Simple features are a single observation of data with some defined geospatial location. These features in R are stored in a special type of data frame. It's a data frame of class SF. SF data frames have two properties, or two types of property. They have a geometry. Geometries are properties that describe the location of a data point or a location of a feature in the data set. Usually it's a location on Earth, but it doesn't have to be. It could be a location in some imaginary space. Like sometimes you'll want to be doing geospatial analysis with multidimensional arrays and things like that. You can plot those things like probability distributions in multidimensional space. You can do that sort of thing. By default, SF really is mostly for two-dimensional data, but it has support for up to four-dimensional data. Four-dimensional data in SF is typically height and time, but it can be any arbitrary four dimensions you want to plot. Geometries are stored in a single reserved column in the data set, which is a special type of column that I haven't talked about in this class because they're relatively uncommon. It is a list column. List columns look like a normal column in a data frame, except each element of that column, so a single observation, single element of that column, is an entire list that contains many, 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 many elements. It could be an entire data frame, right? They have to do this because for a single row, let's say you have an observation for a state in your data frame, well, a state has a very complex outline following, natural geographies and stuff like that, unless you're like Wyoming or something like that, and you're perfectly square or rectangular. Every individual line and point requires its own set of coordinates to do it. So to store that, you need a massive list of information, but it all needs to be contained in a single row of data. The way the SP package did that is that every individual point for that state boundary would get its own row in the data set, meaning old SP data frames would be millions of lines long, because some of these states just have a million different points in them. SF stores it all as one element, which is a list. Because it is a list column, it's harder to work with and modify that geometry column, so special functions exist for messing with it. You can't even use select to remove the geometry column in an SF data frame. It doesn't work. It's like, no, you can't use select on a list column. If you want to get rid of it, you'll have to use a special function I'll mention later. These geometries that are stored in this column also contain a defined coordinate reference system, and I'll talk about those in a second. The other type of element or other type of attribute for features are their attributes. These are the characteristics of the location. In a state, it might be something like the population, the number of people, some characteristics of a city or something like that. Basically, attributes are all of the non-spatial measures. All the columns in your data that do not describe a geometry are the attributes of a simple feature. These are standard data frame columns. So the geometry is something very different from every other column in your data frame if you're working with an SF data frame. Questions about that? We'll see them in practice here in a minute. Okay. So, another thing you need to know about are coordinate reference systems, or CRS. If you see CRS, this is what it's referring to. These specify what location on Earth any given coordinates are relative to. All coordinates are obviously relative to something. Every set of coordinates has some 0, 0, the center of that Cartesian plane. There's a 0, 0 somewhere, right? And if you think about it, any 0, 0 you pick on a globe like the Earth is arbitrary, right? You could go to any point on the planet and plot a Cartesian plane away from that point. Okay. The most commonly used standard coordinate reference system in existence is WGS84, which is, what is it? It's World Geo... It's not World Geographic Standard. It's something... Anyway, WGS84 is the standard for Google Earth and the Department of Defense. Mainly it's due to it being the Department of Defense's default, because what does the Department of Defense run? Global positioning satellite systems, right? So because they did that, they decided on a particular projection that determines how GPS satellites communicate to every device with a GPS receiver on the planet. It's in WGS84 projections, which means damn near everything is in WGS84 because everything we use is based on satellite data for the most part. Okay. There are two ways to define a CRS with geographical data in R. The first is by giving an EPSG code. If you see EPSG, you can give it some number. It'll usually be something like, for instance, WGS84 is 4326. If I have some set of latitude and longitude coordinates and I want to arrange them to WGS84, I would just say coord SF and then EPSG equals 4326. It will reshape my coordinates to correspond to WGS84. You might be asking, well, why do you have to make your latitude and longitude conform to some CRS? Well, the thing is that everything we're plotting for the most part in R is on 2 dimensions, and our planet is a sphere. So no matter how you plot coordinates, latitude and longitude, you are always using some sort of conversion from an ellipse, from some sort of sphere or semisphere, and it's an oblate spheroid, but some sort of sphere to a flat plane. Your CRS, part of that is telling the computer how to convert those latitudes and longitudes on a sphere into a flat surface. And the way that performs is going to be very different close to the North Pole or the South Pole than around the equator. Different geometries or different projections, because they are centered on different parts of the globe, will have more or less distortion. If you're working with geographic locations very close to the North Pole or South Pole, you do not want something that uses as its reference somewhere on the equator. Things are going to be massively expanded on the north side, right? So when I'm working with something like data in Washington, I use Washington State's CRS. It has its own CRS that's centered right in the center of the state. WGS84 usually works pretty well for anything fairly south of the Arctic Circle. Okay. Another way that you can define CRSs in R is with a proj4 string. So this is a string that doesn't just tell it the number, the WGS84, it very specifically says, okay, this is the ellipsoid shape I'm going to use for the planet to convert my projection. It's centered on some particular location. It just so happens that you tell its coordinates that it's going to center on based on WGS84. So it's at 0, 0, 0 because WGS84 relative to WGS84 has a reference of 0, 0, 0. I should have probably picked something other than WGS84. It tells it how to do its projection. It has datums. The datums are sort of what are the actual units going around, and some initialization string. Or in other words, this is just saying, I'm going to use EPSG 4326. Using these EPSG codes in proj4 strings will allow R to go out, if it doesn't have it by default, go out, grab it from a server, get the appropriate projections, reshape your data on the fly, produce the map that you want, and you can use these to jump between different projections. It's important to know about this stuff, even if usually it happens under the hood in R. If you want to merge two different geospatial data sets, they're very often in different projections. You're going to have to make one of them into the same projection as the other one to do the merge, so you need to know that these things exist. Okay, any questions about that? This is sort of a rabbit hole. If you're interested, these are all links you can click on in this stuff and kind of go into the infinite depth of coordinate reference systems. There's a reason there's professional surveyors and geographers out there doing this stuff. Okay, next thing, shapefiles. Geospatial data is normally stored in something called a shapefile, which stores all the geometric data as just vectors with associated attributes, more or less simple features. Shapefiles, unintuitively, usually consist of multiple individual files. There's usually at least 3 of them in a given shapefile. They are a .shp file, which has the actual geometries. That is, it has the outlines of states or counties or whatever, or it has the points that things occur at. It has a .shx file, which is a shape positional index that sort of tells where they are relative to one another. And they usually have a .dbf. The .dbf is just a database 4 file. It's like a 1970s, 80s standard that has binary data storing all of the sort of non-geospatial columns. This dbf file is essentially the same as like storing columns in a .rdata file when you save a data frame. They usually come with that if they have anything other than geospatial stuff. And often there will also be a .prj file, which is the projection or the coordinate reference system. They just store them all in different files. Sometimes you'll get only a .shp file, and R usually plays nice with that, but normally you come in a whole package. Sometimes there'll be like a dozen different ones. Every additional file just conveys some additional information to R or the GIS software to put stuff together. Yeah, so normally you'll see that. If you see a .shp file like that, you immediately know you've got probably, some shape file that can be read by R. So if you get geospatial stuff, ideally it comes in a .shp file. Okay, so to actually use SF, now that you've filled your brain with trivial knowledge, there's a lot of functions in the SF package. It is an enormous package with a couple hundred functions, I think. I'm just going to display a few of them today and talk about just a few. So ones you're going to have to use if you use any kind of shapefiles, you need stread and swrite. These read and write shapefiles. It used to be hard to read in shapefiles that were made in like ArcGIS, QGIS and stuff. You had to tell R all sorts of very specific things. These functions work like magic. You just give it the location on your computer of the .shp file, and it goes and tracks down all of the related files in the same directory, stitches everything together, and outputs a tidy format like geospatial object. That is voodoo to me. It's amazing that it just does it, but it just works. Other things you'll want, GeomSF. There is a single geometry function for ggplot that does all of the geospatial plotting you'll ever want. GeomSF does basically everything. You just do like plus geomsf, give it aesthetics and things, it plots stuff. We're going to see a lot of that in a second. ST join does spatial joins. Well, we did lots of left joins, inner joins, all that stuff when we're working with dplyr. This is for doing spatial joins. Spatial joins can be really complex. You could say have a data set where you have a whole bunch of points, like a whole bunch of maybe you've got a whole bunch of households, and you want to merge it onto census precincts, or not census precincts, but census tracts. You could say, I want to join this data set to this data set based on being within those points. And so all the points here, whatever precinct, or not precinct, but whatever tract they lie within, it will merge their data onto that particular tract, or vice versa, take the attributes from these tracts and assign them to those points. So there's directionality to it. It just stitches them together. It can also do fuzzy joins. Like let's say you have boundaries. This is something that Steve in the back was working on the other day. Is that if you have, let's say we've got some census tract, they're never a perfect square, but if it looks something like this, and you want to merge on elections data to that, well, those precincts do not have contiguous boundaries with that. Your precincts might look like something like that. Well, how do you merge the data on? Neither of these are fully within this thing. They have overlapping. You can do a join on this in a lot of different ways. You could say, for instance, instead of just joining the data, I want to make it so every one of these election precincts contributes a proportional amount of information to this underlying tract, proportional based on the area of that precinct. You could do that with ST interpolate AW, which is aerial weighted interpolation of polygons. It's a lot of big words saying, okay, let's imagine that this right here is wholly 60% of this set tract. And then these ones are all like, not 20, but let's make them all, well, what would that be? That would be like, wow, I'm bad at math today. This is really bad. But they're all like, I'm just going to pretend this adds up. Okay. Let's make that 55. Okay, so let's say 15%, 15%, 15%. What the aerial weighted interpolation can be told to do is, let's assign to this tract, let's say that 55%, so this tract will contribute to 55%, say, of the votes that occur within this tract. This one will contribute to 15%, 15%, 15%. This creates a weighted average of all of these different districts in its contribution to this particular tract. This is mathematically very complex to do and would be really crazy to do if you have, say, like you do in Seattle, like 2,500 election precincts and 122 census tracts, right? But it can just do it all by figuring out how these things should be distributed and proportionally assigned to things. So you can see spatial joins and like spatial data mapping to things can be much more complex than doing conventional joins in dplyr. The SF package takes care of these things in a really user-friendly way. Other things you might want to do that are simple. ST transform converts between different coordinate reference systems. As I said before, you can't do merges unless things are using the same coordinate reference systems. You'll have to change them. ST set geometry period null is something you'll want to remember if you want to get rid of geometries. If you're working with an SF data frame, some dplyr functions do not work on SF objects because they have that list column. If you no longer need your geometry, pipe your data frame into this .null. This removes that geometry column from your data frame. You can't just select and minus remove it because it's an integral part of the data frame. This allows you to delete that geometry from a data frame if you no longer need it. Say you were doing something like this, and the only reason you needed the geospatial data was to do this aerial weighting, and then afterwards you're not going to map anything. You might want to get rid of that geometry. That's how you do it. Next, ST-relate will compute relationships between geometries. If you're somebody who does spatial statistics, you probably want things like neighbor matrices and stuff. ST-relate will let you come up with different ways to calculate neighbor matrices. Neighbor matrices are just like, for every individual observation in the data set, you want to know which other observations border it, because you want to say, oh, maybe there's spillover effects. In crime, we do this a lot where we're like, okay, crime in a neighborhood or the effect of crime in a neighborhood is really not just what's limited to that neighborhood, but there's also spillover effects from adjacent neighborhoods. To get that, we need to know which neighborhoods are adjacent to that one. strelate would allow me to generate that information. Okay, so obviously there's a lot of really complex stuff, and I'm not going to go through how to use all these different things because they're crazy, they're complicated, they could have their own entire days associated with them, but this is all within this one package, SF. It's a huge package that does everything geospatial. It's pretty awesome. Okay, so I'm going to do some simple examples using data we've used in the class just to illustrate sort of the power and the ease with which we can do stuff with SF. So first thing, I'm going to work with the voting data from homework 5 that we remember unless the trauma caused us to block it out. You can get shapefiles that link up for those voting precincts from the County GIS data portal, which is what I've done. And I can load them in using stread. All I have to say is stread the location of the .shp file, and here I say strings as factors equals false. This was something I talked about in like week 2 or 3. By default, most functions in R, when they load in data, look at character data and automatically convert it to a factor. I don't like automatic factor conversion, so this is just saying don't convert it to a factor. Then I just say I'm going to select only the precinct names and their geometries because I don't care about all the additional information in the shapefile. What comes out is something like this. This is output from this function telling me how it read the data in and what we got. It says this is a simple feature collection, so it's simple features geometry with 2,592 features, 2,592 precincts in this data set. Which remember back if we looked at the King County data, that's how many we started with. Its geometry type is multi-polygon. They're all polygons with many points. And in fact, there are multiple sets of polygons for each one. Its dimensions are only x, y. There's no height. There's no time. It has a bounding box. The bounding box has some numbers. There's some kind of coordinates relative to some projection. It has no EPSG code associated with it. It's not like in WGS84. But embedded in that shapefile is a proj4 string that says, oh, well, all of these coordinates, these numbers, are in these particular units relative to some latitude and longitude and location. That's because these precinct data are coming in Washington State's standard projection, which I could then convert to WGS84 or something else. Okay? All this information is useful, but it might look like gibberish. It's okay. If you do a lot of stuff with geospatial data, you get used to reading this and being like, oh, okay, this is informative. Okay, but that's all you have to do to read it in. Okay, now there's a shapefile lurking in my global environment. Okay, quickly, I'm going to process some data to merge onto it. This giant wad of text here is pretty much your entire homework 5 compressed into a single function call. So what I'm doing here is I take the original elections data, I'm filtering down to the presidential race, the Seattle tracks, I'm selecting precinct counter type sum of count, if you remember all those variables. I filter down to only the presidential candidates I'm interested in, Trump, Clinton, plus registered voters times counted. I mutate them to give them different, I recode the counter type rather to give them different names. I spread the data out, because by default they're in like one column, keys, values, I spread them out into multiple columns. I mutate percentage Democratic vote, percentage Republican vote as a proportion of votes for Clinton over total votes. I get a turnout as total votes over registered voters. I select it down to the columns that I want. I filter and remove missing values. And then all I have to do to merge all of this onto that precinct shapefile is say left join. All the precinct names are the same in these two data sets. I say left join. Now it's a geospatial data frame. Okay? So, my data set now looks like this. I have precincts. We remember these precinct codes from the homework. SEA something. They're all Seattle ones. My percent Democrat votes, percent Republican votes, my turnout percentage, and then I have this other column. I have a geometry column, which says things like multi-polygon, US survey foot, multi-polygon, and then a bunch of numbers associated with it. This is slightly informative. This tells me the units of these polygons are in survey feet, so they're in US standard feet distances instead of being in like latitude, longitude units, which is a really different unit if you think about it. A foot anywhere on the planet is exactly the same distance. The difference between a longitude unit and every part of the planet is completely different. As you get further away from the equator, longitudes get smaller and smaller per unit. So this is a standard linear unit that's the same all over the planet. I'm going to convert it to a less standard unit in a bit. Okay, so we can plot all of these precincts really simply. All I say is ggplot, these precincts vote data, AES fill equals % Democrat. Then to plot the geospatial, I just say geom_sf, and then I'm adding on a little bit of stuff to make it look nice. I say color equals white. Color is going to set the boundary lines around the precinct. I'm doing white because it'll kind of highlight them all in white. Size 0.1 to make the lines really small. I do datum equals null in coordinate SF because otherwise there'd be a whole bunch of graticule lines, which are basically the latitude and longitudes plotted left and right and up and down in the background. I don't like how those look, so I deleted them. But it just plots the thing. It just works. geom_sf takes all of the geometry information from all those different observations and converts it into a whole plot. This is all, I don't remember how many exactly. I know that there's like 2,000 something King County precincts, but there's like 1,000 inside of Seattle. It just plots them all, plots them quickly, accurately, nicely. They're filled by color by the percentage votes everywhere. Yeah, it just works. This is so much easier than plotting an SP where I have to do all sorts of data frame shaping to squeeze it into a ggplot. Because SF stuff is already in a tidy format, it just works with ggplot. Huck it in there like it's any other data. Anyone have questions about any of the stuff going on here? Yes?
Any ideas why I'm getting a projection error?
What is it?
The sample code. Seattle is squished vertically.
It's squished vertically. There's a couple reasons it could be squished vertically. You could say there's a add-on geometry called it's chord_fixed or chord_equal or something like that will automatically unsquish things. You'd have to check. It's a good question. It would depend. I'm not having a problem, obviously, in here where it's squishing it, so that's a good question why yours would be coming in squished. So are you producing it in the RMD file, or are you printing it to your viewer?
RMD file.
Okay, if you try print it to your viewer and see if it's squished there, and then reshape the viewer and see if it's changing shape. If it's changing shape with the viewer, you probably have to apply something like to fix the coordinates at their correct ones. I'm not sure why mine does not do that and yours does it, though. That's a good question. Any other questions? Yeah.
Legend top position is
Bottom. Oh.
I give up.
Yeah. I moved the legend down to the bottom on here just so that this otherwise would have been squished, but yeah. Yeah. It's kind of cool. Okay. That's about it for simple SF plotting. I'm now going to show the rest of the SF stuff using the Tidy Census package because it is super cool. Okay. Tidy Census, one of my favorite packages. Okay. So Tidy Census can be used to search the American Community Survey and Decennial Census for variables, then download those variables, automatically format them as tidy data frames, and grab geospatial data along with them. So these data frames, if you give it an argument, geometry equals true, it will also spit out a shapefile with it automatically in this nice SF full tidy format. Okay. This package utilizes the Census API, so the application program interface. I've said API a bunch of times, but because I'm stupid, I left talking about what an API is to this slide. To use this package, you need to get a Census API key. Unlike almost every other place you'd apply for an API key, it is really stupidly easy to get a Census API key. You click on that link there, and you type in, I think you just type in your email address, and then click a button, and it gives you an API key with an unlimited number of requests. You don't have to do anything special. U.S. government data. It's actually the most shady-looking website, though. I'm actually going to click on it. That is their request an API key, right? This looks like the kind of thing that if I fill numbers into, it's going to steal my credit card information. But you just say, what is the name of my organization, my email address, and do I agree to these terms of service? You press a button, and it spits out an API key. Just spits out right on the page. That's all you need to do it. It looks super shady, though. I love it. Okay. I don't even know if you need a real email. It might send you something, but I don't remember if it does. It's just super there's whatever, it's census data. I mean, census data, of course, by definition, has nothing identifiable on it. There's almost no nefarious purpose you could come up with. They just do it to prevent people from doing denial of service attacks on the Census Bureau by limiting requests to being something with an API key. That's really all it's for. They don't like it if you do like 10 million requests in a day type thing. They're like, just shut it, stop it, and that's about all it's for. Anyway, so I have a more in-depth discussion of APIs in my social media data and text mining lecture, which I'm not doing this term because it's really hard to keep up to date with all of the text mining and social media data stuff. But basically, an API is a type of computer interface that is the native method of communication between computers. Your computers, when one computer is talking to another computer, it's usually doing it over some kind of API. You can directly access APIs in R using the HTTR package to make API queries back and forth. Your browser does all of its stuff through sending API queries to like the server you're talking to. They're usually done over HTTP. Hypertext Transport Protocol is just an API for communication between computers. Okay. Well, HTTP is a communication method that links APIs. Anyway. Yeah, most R packages that interface directly with websites and databases will be using some API under the hood. APIs can be contrasted with scraping. Scraping data is when you're pulling data off of websites and stuff without using an API, rather using human-readable text and extracting parts of it. The API is getting the stuff underneath the hood that generates that human-readable text. Anyway, APIs make it easier for you to access data, while at the same time making it possible for those websites to control how much data people get and how they get those data. Yeah. Okay. So, there's a few key functions in Tidy Census. The first one is Census API key. You give this function, the Census API key that you got from the census, you run it, and then you can tell it to save that Census API key, and you won't have to put it in again. It just saves it in this version of R. You can do all your queries and not need to put it in again. It's kind of nice. Next is load variables. What load variables does is you tell it which survey that you want, that is like the ACS, the decennial census, what year you want, and it will produce a data frame that has a list of every variable in the ACS or the census for that year with its label, its variable name, and its description on that particular variable. Well, the census and the ACS have thousands and thousands of variables. This makes them come in a nice data frame. Well, the cool thing with a data frame is you can use all that string stuff you learned last week to do searches on all those variable names, labels, and stuff. If you want some particular concept, like you're like, well, I want the number of 18 to 25-year-old white men in a census tract, you could search for you could say string detect 18 and male, and you'll get all of the different variables in the data set that have those words in them, so you can search through them and find the variables that you want. This is kind of nice. If you already know what census variables you want, say you've been using American Fact Finder on the census or something like that, you can just give it those variable names and it will pull them up. Okay. Next, there's two functions that have the same arguments, get decennial and get ACS. Get decennial loads census variables and their geographical boundaries. ACS loads those ACS variables and their boundaries. You give it a variables argument and you provide a vector of the variable IDs that you want. These variable IDs, you could actually just subset the output of load variables, grab the column with those IDs and pipe it straight into variables down here to get the variables that you want. Right? You can just use that. You give it a geography. Geography could be something like, oh, I want my variables at the state level, the tract level, the block level, the county level, whatever variable level of unit analysis you want. You give it a year. Tidy Census has access to the 1990, 2000, and 2010 censuses. And it has ACS going back about that far too, actually since the start of the ACS. Yeah. Then, if you want the geospatial boundaries, you just say geometry equals true, and it will return already SF formatted geometries for every unit that you get it. This is pretty cool. This saves all of the work involved in going through the American Fact Finder, grabbing variables manually, going downloading shapefiles from somewhere, knitting your stuff into your shapefiles, trying to make it into a tidy format. It just does it. It makes it look so easy that it's kind of offensive to somebody who used to do all this stuff manually. I'm just like, shit, it just works, right? It's amazing. Okay. So, here's an example of searching for variables. So, you see here I have commented out Census API key. I've already input my API key here, and I'm not sharing my API key with you guys. If you have an API key, don't embed it in any documents that you have, because that means if you share those documents, other people have your API key. For the census, that might not be a big deal. It can be a really big deal if you do research on something like Twitter or Facebook, because your Twitter and Facebook API keys don't just allow people to download data, they also allow you to post to your profiles. Do not share your API keys for social media stuff. Anyway, so I use load variables, and what I want is I want the 2015 ACS 5-year estimates. So I'm saying ACS 5, 2015. So this is going to be values based on the American Community Survey from 2010 to 2015. The end year is 2015. Okay. Then as an example, so I've loaded these variables up. I'm just going to print rows 10 through 18 of it. This is what it looks like. I have a variable name, the census variable name. I have some label on it, for instance, estimate total male 20 years, and then some concept. Sex by age. So this is the number of males of age 20 in this particular geometry, and this geometry is census tracts, because that's what I've told it to get. Or it's what I'm going to tell it to get, rather. Okay. This data frame, though, is massive. This ACS 2015 VARS has, I think it's like 2,000 or 3,000 rows of variables that you could get. It's massive. Tons of cool stuff. And you can just search. So instead of subsetting this way, I could say, like, string detect something and then find all of the rows that correspond to it. Then I can just grab the variable numbers that I want and put them into a query to get the variables. Like this. What I want to get is I want to get ACS data in King County at the tract level. So I say, get ACS, geography, tract, that is census tract, state of Washington, county, King County, geometry true, because I want those boundaries for all of the census tracts. Then I'm only asking for two variables. I'm asking for B02001_001E and 2009-001E. What are those? These are the total population and the total population of people who have identified as Black or African American in these tracts. Okay? So I make this query. It outputs an object called King County. I'm going to look at what King County looks like. It pops out with this, a GeoID. The GeoID is the universal code for geometries in the United States by census-like measures. 530-33-00100 tells me 53 is Washington State, 33 is King County, 100 is tract number 1 in King County. So it says down here, name, census tract 1. Oh, that's right, King County. Yep, Washington 1. The name lines up with what I understand. Then we have columns, variable, estimate, and MOE. So the way these data come in by default is in a very long format where your variables, the individual variables, are all embedded in the same column. So for census tract 1 in King County, there are two different measures, because there's two measures for every tract. This variable and this variable, these are the values for those two variables. So this census tract has a population of 7,261 with 1,271 Black individuals. Then it has MOE. This is the margin of error. If you want to put confidence intervals on census data, they already come with those confidence intervals, the margins of error. So you could just say 7261 plus minus 479. That margin of error is, I forget if the census defaults to a 90% or a 95%. I think it's 90%. Yeah. Then there's that geometry column, which is that multi-polygon geometry down here. This one you'll see pops out in normal latitude and longitude because by default these things are spitting out in WGS 84 standard latitude and longitude, I think. Okay. So my variable names are down here in variables. My values are in estimate. If I have data formatted like that and I want to make them into columns for each variable, what would I normally do? I'm going from long format to wide format. Yes, it is spread. I'm going to spread my data. So what we're going to do is we're going to process our data to get one row per precinct, because right now I have 2 rows per precinct. This is the same, not precinct, but tract. I should say tract, not precinct. Bad check. But okay, I'm going to spread those. So what I do is I say King County. I'm going to get rid of the margin of error column. I don't care about my margins of error, and it makes it easier for me to spread my data if that column is no longer there. I'm going to group them by their GeoID, so I'm going to do some sort of operation once on each GeoID. Each GeoID is a census tract. I then say I'm going to spread the variable and estimate. Then I'm going to rename these variables because B02001 underscore 001 is now a column name. I want to change that to total population. I want to change that one to any black. Then I'm going to mutate this variable so any black is now a proportion. Any black divided by total population, which gives me a percent black, or actually rather a proportion black in a given census tract. Okay? This is what the data look like now. If I get head on them, when you get head on an SF object, it always starts out by giving all of that geographical projection information up at the top. This is one way you know it's a totally different type of object than a normal data frame, because it spits out summary info even with head. Right? It has a bounding box. It says it's in 4269, which is NAD83 projection. Anyway, I have a GeoID column. I have the name of the census tract. I have the total population. I have the proportion black, and I have a geometry column. Well, that's everything I want to go spit it into something to mapping. I have one row per tract. Just plot these. To do that, I'm going to spit them into some mapping code here. I say King County, pipe it into ggplot. AES, my fill equals any black, so that means I'm going to plot a bunch of geometries, but the color inside of those geometries, that is inside of the tract boundaries, is going to be based on the number of any black, or the proportion black in that tract. I say geom_sf, again, size equals 0.1, color equals white, because I think thin white lines, boundaries, just looks really nice. Do whatever you want. Then I say here, coord_sf. This allows me to modify the coordinate reference system inside of the plot if I want to plot with a particular projection. In this case, I wanted to go from NAD83 to WGS84, just because I do everything in WGS84. Looks nice. And so this is the proj4 string. Proj equals long lat, datum equals WGS84. Datum NA over here removes those graticule lines I was talking about. I don't like those grids. Then I say scale fill continuous. This is me saying, okay, I want, as the number of black people, as the proportion of black people in a tract increases, I want it to get closer to this color, and as it drops, I want it to get closer to this color. These are hex codes for colors. I'm really anal about colors, so I actually went and looked up particular hex codes that would match my slide colors nicely. You could put in colors like black and white, and it'll work just fine, but that's what I tend to do. Then I gave it theme minimal, GG title. Some more information on what I'm doing exactly up here. Are there any questions about any of the oddities I've done up here? It's pretty straightforward, except for this line, basically. Okay. Well, it looks like this. This is all of King County. Any black up to about, the highest proportion black anywhere in King County is about 42% or something like that. You can see it's highly concentrated over here. You can tell that this is like Puget Sound is all this area here. This is the Bay. This is downtown. This is southeast Seattle. Yada, yada, yada. You might notice, however, that if you look at this, that we know that somewhere up in here, this should be Lake Union. We know there's a huge lake over here, which is Lake Washington, which just looks like census tracts and stuff like that. If I look at this plot, it's actually hard for me to see where Seattle proper is because the water is just filled in because census tracts actually extend out into the water. That's just the way they're defined, right? Well, I don't like that, and so we can deal with that in a special way. We can remove the water from these plots by downloading a file that has the boundaries of the water and subtracting the water geometries from the existing census tracts. So there's a function I put together right here that will remove water from any geometry you give to it, provided you can find water. This function is st_erase. This is somebody actually got off of somebody's Stack Overflow page, I think, originally. I modified it slightly, but it's a great idea. So this has a few functions that I'm not going to get too much into, but they're all required steps in this to make this work. So what this function does is, given an x and a y, it will first take the y that we put in. The y that we put in is going to be water, the boundaries of water. It will take all of the different water boundaries. So every body of water has its own separate boundaries. I want to merge them into a single object, so it's just like one big layer. stcombine will merge them all together. stunion will resolve any conflicts in their internal boundaries in case some of them overlap. That's a common thing, like the lines are imprecisely drawn, so they'll sometimes overlap. They'll give errors if you don't resolve those internal issues. Then ST difference will subtract the thing over here from the thing on this side, which is what we want to do. We have boundaries that have all of the water kind of drawn over, and we want to remove this stuff. This essentially just cuts y out of x. Okay? So I need the water geometries. This is how easy it is to get a geometry of the water in R. I say Tigris, which is a package you've never seen before and will never call on directly, but if you've installed SF, you have it. Tigris is for calling and getting shape files of all sorts of different kinds. I'm saying Tigris, I want area water. This is going to give me all the boundaries of water in Washington State, in King County, and I want it to output it as an SF object. It just works. It goes and downloads it online, pulls the files down, formats them properly, and spits them out into an object. So KC Water is now an SF data frame with all of our water boundaries. Then I say, take my King County data frame, which looks like this when plotted, pipe it into ST erase. So that means King County is X, KC Water is Y. So it's going to take King County and subtract KC Water from it, which is King County Water. And I assign it to King County no water. I then run the exact same plotting function as the previous page on KC no water. And now it looks like this. We've removed every body of water in King County. And now it looks probably more familiar to people who know what King County looks like from orbit, right? We have Lake Washington, Lake Sammamish. We actually have the Duwamish River. You can see Harbor Island here. Every river and lake is cut out all over the entire county. That's pretty cool. That cut out a lot of stuff and made a really nice looking map without us ever getting an actual, like, the shape file by default that had all the water cut out of it. We just created our own. We can knit together geometries using some basic functions. This would be much harder to do without SF. It's trivial to do in SF. It used to be so hard to do. Okay. This right here is the type of map. If I wanted to put in, say, the distribution of the black population in King County in a publication, I might make this black and white, but I would send this in with the water and everything. It just looks really nice, right? Put this on a website or something. Just works. And it doesn't take much code to do. Any questions about that stuff? That's about it. As a reminder, Homework 6, Part 2 was delayed a week, so it's due next week. There's also an optional homework using mapping of restaurant inspection data. If you're interested in that, you might wait a minute. I need to look at that homework and make sure it's updated properly for GGMap. It's not required, it's optional. I will give you extra credit points if you're somebody really into points. It's not like anyone's failing my class or something like that, but if you like the approval of receiving 2 or 3 points for something, go for it, I understand. Yeah, that's about it. Any questions?
Oh, so if you want to do a join, is it just like join? I think I saw that.
Oh, join the geometry, or join 2 different data frames, one of them having geometry?
Yeah.
Yeah.
Well, no. Well, like, say I had like data on like, I don't know, for, like point counts, like per county of like
Mhm.
so something like that. Can you just join it in like using like dplyr?
Kind of. You can pipe in, but if it's geospatial, well, okay. Are you joining 2 different geospatial objects?
No, it's just the data frame to like overlay, like maybe get a frequency of like
Yeah.
portion of depths for a region.
Yeah, if you've got, I mean, as long as they both have a matching column, it's a normal left join.
Okay.
Yeah, if you've got something like the census tract number or name, you could just join that way. If they're both geospatial, you have to do a fancy ST join. But as long as only one of them is spatial, you just join by a column.
Is it still pretty good at doing ST join? Like if you wanted to combine like a map of Oregon and Washington?
So that's not a join. That would actually be essentially a bind. So a join would be they overlap in some way, and you have to figure out how to assign them appropriately. Is a join. If you just want to put 2 things together, you literally just would basically R-bind them. As long as they're in the same coordinate reference system, they'll just stick together. Any other questions? Okay, you can leave.